Welcome, Charles Zhang. I'm going to talk to us about the design of an efficient Lisp bytecode machine and compiler. You have to hand it to him.
Can I use it? Okay, so yeah, I'm Charles Zhang. I did this work on an efficient Lisp bytecode compiler with Alex Wood and Christian Schafmeister, who supervised the project and also contributed to some of the virtual machine and a little bit of the compiler. Yeah, so this was a group effort. I did the design for the bytecode machine and worked on the compiler, and Alex also worked on the bytecode compiler and a lot of the virtual machine, and also the C++ translations of those. So I'm going to talk about the motivation really quickly because there are so many bytecode compilers out there. Why are we doing one? And the simple answer is we want to make bootstrap in class faster. This has historically been a huge problem. Even last year, after a lot of work was done on this problem, it still took about 150 minutes of core time on a very beefy computer to bootstrap the entire implementation, which is not very good if you're always developing this thing, and it's still very rapidly in motion. This implementation is updated very frequently, so having build times be long is kind of a hindrance. So that's why there's so much effort being spent on it. And especially if you look at how the compiler bootstraps itself, we can really see that it's not very simple. But before this work was done, how the compiler bootstrapped itself was that first you have a very basic S expression walking interpreter written in C++. Then you have a pigeon compiler, which is written in Common Lisp now, but it doesn't really have lots of features, and compiles straight down to LLVM, which loads the Common Lisp object system so that it can load the real compiler, which is written with the Common Lisp object system, and then it self-builds itself. And in the end, you have a LLVM native code compiler. But yeah, this process does not is not a speed demon. And so what we thought was, okay, so at least for the full compiler, there was a lot of work made on parallelizing it. So if you, for example, had a machine with many cores, you can speed up this end of the pipeline with parallelization. But especially when you have an interpreter and then you have like a pigeon compiler where parallelization isn't there, this is kind of like a serial bottleneck in your pipeline. And we thought that we could perhaps just replace the interpreter and pigeon compiler with a bytecode compiler, because the idea is that a bytecode compiler is still simple enough, like an interpreter, to run and execute forms, but it's going to be faster than trying to run a full compiler on an interpreter. So that was the hypothesis. Also, LLVM is kind of slow to compile. It doesn't generate slow code. I think it's actually pretty good at that, but yeah, you have to hand it LLVM IR, and it has to crunch through it, and no amount of Lisp magic can really help with that. It's kind of a project that's maintained by a ton of people, corporations, out of the control of this small group of programmers. And the other thing that kind of motivated was that not all code needs to be native code fast. You think about like UI, interface, debug functions, things like that. Native code also takes up a lot of space, so another motivation for bytecode compilers in general is that you want to have this code be small, not really take up that much space, don't want to take too much time just compiling it. And so yeah, like I said, this is not new conceptually. Bytecode compilers and interpreters have been around forever, so I'm just going to cite some of the previous work done in the Lisp domain. Even the most famous handbooks and textbooks in this area cover bytecode compilers. For example, Structure and Interpretation of Computer Programs, written by Sussman and Steele in '84. By the way, Sussman is the next speaker, giving the keynote. Lisp in Small Pieces, which is kind of the book on Lisp compilers and interpreters if you want to learn how to craft these sorts of things. There's a bytecode compiler in there. And not only do textbooks give introductory material into bytecode compilers, you also have implementations that already do it. So CLisp is a full implementation that runs just on bytecode, initial version 1987. ECL has a new one now recently. CMUCL also has a bytecode compiler supplementing the native code compiler. So it's really interesting. We want to see why we created a new one when there's so much that has been done before. Well, the constraints are a little bit different than the previous common Lisp implementations we talked about. First of all, we're really thinking about Bootstrap. A native code compiler already exists, so we don't necessarily want to do a lot of optimizations. For example, CLisp has multiple optimization passes because it has no native code compiler. CMUCL's bytecode compiler is for a very different reason. They go through the same semantic front end, so it's not optimized for compile time, and it's designed really for space. I think in the CMUCL manual it says that bytecode compiled functions are about 60 times smaller than 32-bit machine code. For 64-bit machine code, it would be an even bigger space saving. So ECL's bytecode compiler, I believe, fits the bill here. It kind of has the same motivations, but we didn't use it because there are also some things specific to the C++ aspect of class, which is that the virtual machine needs to take C++ exception handling into account for local, non-local exits. An interesting feature about the class compiler is that an implementation is that it interacts kind of seamlessly with C++ code, and C++ exceptions are handled just as if they were Lisp exceptions when you're doing stack unwinding. And also, I personally have some experience working with CLisp in the past. I wrote an optimizing compiler middle end targeting the CLisp virtual machine. And so I sort of saw things in the virtual machine design that could be improved. In particular, how to make execution speed faster without sacrificing compile times. I'm just going to go over some of the high-level design decisions because I think we made some interesting and different design decisions from a lot of the previous compilers. So I think the most important thing I want to say now is that we don't want an IR for this bytecode compiler. It's meant for Bootstrap. Having an IR means you need to have IR structures, you need to cons IR structures. For example, a NanoPass compiler, a lot of it is just the memory and keeping different translation stages and having different representations you have to go through. If you have so much memory, it means you have to cons that memory, and the garbage collector in Clasp is actually not amazing, so even consing is slow. It's not a bump allocator. And also, it makes the compiler simple. When you don't have optimization passes, you can conceptually think of it as a straight line execution, almost just as if it was an interpreter, but instead of executing it while it's walking the tree, it's just emitting bytes. That's pretty much what this bytecode compiler does. It just runs through your S expressions and produces bytes straight away. That's the mental model. So the central question is, we have such a simple compilation model. How can you actually generate code as fast as possible to do this? And what we decided to do was to make high-level data structure and representation designs that facilitated using this simple model, but still emitting efficient code. We use the flat closure representation, which is actually almost never used or described for simple compilers. None of the bytecode compilers outside of the CMUCL one actually uses the flat closure representation. It's not even mentioned in the handbooks, this approach, not in Lisp in small pieces or structure and interpretation of computer programs. I'll get to what flat closures are in a moment. And also, we make this design decision where we co-allocate the code for functions compiled together into the same bytecode vector. What that essentially means is that if you have a function and you have an internal function in that function, like a local function, the bytecode for those is in the same bytecode vector rather than being separated bytecode functions. And the reason we did this is that it reduces the complexity for the virtual machines instructions for handling non-local exits. And I'll also get into more detail later. So yeah, the optimal compilation strategy for these representations, the reason why it's not used in simple implementations, is usually because it requires some form of IR and some kind of analysis over it. We actually can do this. We found a way to do this with with assembler techniques and fix up data structures instead, and I'll make that more clear later as well. But that's the high-level picture. So I talked about this flat closure stuff. I also want to say flat closures are not a new thing. They've been well known since, I think, before the mid-'80s. But for those of you who have never seen it, I just want to give a quick example. If you have closures, for example, maybe very nested closures like this, if we recall from creating scope diagrams to model how the environments in Lisp work, you have this inner closure can reference stuff in the outer environment here. This closure can represent stuff in the environment here. And then you can kind of map out what the environments for these things look like. In the linked closure strategy, this is sort of the more traditional diagrams we see in those textbooks, which is, okay, you have this lexical scope contained in this lexical scope, contained in this lexical scope, and these are how the closure variables get referenced, which is you walk through this linked list of scopes and you get the variables, and everything's like how we learned it, how to visualize local variables and scoping. The flat closure strategy takes a different approach, which is the environments are modeled as just flat vectors. And this has a lot of advantages because it means you can just do constant time accesses into vectors which close over all the variables that you have in your lexical closures. And an oddity here is that we actually have to create a layer of indirection. We have to create a cell, because in Common Lisp you can set Q variables that are closed over, and these behave like memory locations. They need to be seen everywhere. And here it's fine because you're just referencing each variable. You can directly mutate the bindings in these environments that are closed over as linked lists. But in a flat closure place, just because it's closed over here, if you change the array, if you change this linear array, if you change what the value is here, it doesn't get propagated to the other environment. So you need to introduce a little indirection here. That's what the cell is.
Is it also the case that the linked environment strategy could hold on to objects that are in fact dead?
Yes, great. Thank you for pointing that out. That's a very good point. This is another huge advantage of having the flat closure strategy. This term is called safe for space. As Robert just pointed out, in the linked closure strategy, it could be the case that the outer frame, the very outer frame, contains variables. I think in this example, actually, the variable b is never used. And let's say b contains a huge object. With the linked closure strategy, you actually need to keep a reference to b, because this inner closure, even though it doesn't reference b, it is holding on to that through this linked list structure. Whereas if you use flat closures, you don't need to hold on to that because you only close over what you need. And this allows memory to be garbage collected, objects to be garbage collected, really when they go, when they're not live anymore. So that's another big advantage. So I'm going to move on really quickly from closures because there's a lot to get through, and I'll come back to it later when we talk about how we actually did this. As opposed to the simple compilers from before, as opposed to the other simpler compilers that don't use the flat closure strategy. We also handle non-local exits in an interesting fashion because usually when you're implementing a new Common Lisp implementation from scratch, these are the trickiest operators to implement: tag body, block, go, return from. And so when you're designing a virtual machine, you need to think about how can we design the virtual machine such that these constructs in Common Lisp are efficient, and you create orthogonal instructions to represent the semantics as best as possible. So we actually use much simpler and faster virtual machine instructions than the ones in CLisp or ECL. So first of all, the decision to use flat closures means that you reduce the number of operands you need to get the block or go tag you need to actually return to. The dynamic environment is saved, and you need to save it in order to unwind to the context and restore, for example, any stack pointers. We also have this decision to co-allocate bytecode that I talked about earlier. CLisp and ECL have to close over the program counter to return to the place that it needs to go back to. So, for example, if you have a lambda that goes to a tag not in the lambda, in like an outer function, it needs to figure out where do I actually jump to in the code. Because we co-allocate all the bytecode, it's just a PC relative jump. The code for the outer function is co-allocated there, so you can just statically know where do I need to go, and you don't need to do any closing over. So that also significantly simplifies how you actually do the control semantics of I want to jump to this place in a function that's not in the same function as the place I'm returning out of. So that actually simplifies it quite a lot. I think CLisp, for example, has 8 or 9 instructions in total to do non-local exits, while we only need 3, because we've separated out the concerns orthogonally, because we are also able to unify tag body, go, block, and return from. So I think this is kind of a strict improvement over the virtual machines, the instructions used in the other ones, like CLisp and ECL. And so how did we actually make these decisions? I alluded to earlier that we don't have an IR. For example, flat closures are usually implemented by doing a free variable analysis over IR. And especially if you want to eliminate as many cells as possible, you want to do an ahead of time analysis over IR. So we use this idea of, okay, we don't want an IR, we want to have this straight line model, but we do want to do some optimizations. We already need to do a sort of fix up in the assembler. Recall, if you have a bytecode compiler and you're doing assembly, usually you have symbolic labels, and you need to resolve those symbolic labels into actual offsets into code. So choosing the smallest size for labels needs to be done in any kind of assembler you have anyway, like byte compilers or whatever. You need to have some sort of way to resolve the actual positions of symbolic labels. And we still want, but we want to do these optimizations, which are usually done in IR. The flat closure cells, also choosing whether we want heap allocated cells for non-local exits. So we have these fix-up data structures, which are very standard in assembler technology. We designed fix-up data structures to facilitate all 3 of these. And this still works in the context of a single pass assembler. You can also recall that assemblers are usually just split into 2 different types. 2-pass assemblers, which you resolve all the label positions first and then you emit the assembly code, or a 1-pass assembler where you just do it all at once with fix-ups. So we wanted to keep the 1-pass strategy, so we have these fix-up data structures that can handle all 3 of these things at once. The technique we came up with is optimistic. So the fewest number of cells are emitted, and the label size are actually good as possible. A lot of assemblers are actually pessimistic, where they start with the worst case scenario and try to get better and better positions, whereas we start with the best case scenario and expand the assembly code conceptually. And this way, when you start from the best solution and you try and make it go up, this way you actually do get the best result. And this allows our optimizations to actually just be done directly on the assembly stream in place without any copying until the end, which you need to do anyway. And doing things in place means you don't need to cons up garbage, which is very important for us in terms of getting everything just bootstrapped really fast. And actually, as far as I can tell, I looked at the other bytecode compilers that exist. I don't think anyone uses this idea of like folding in these optimizations that are usually done on IR into the fix-up pass, which usually only handles things like label sizes. So I thought that was actually pretty cool. And okay, so now we're coming to the results. Actually, how are we doing on time?
5 minutes.
Okay, 5 minutes. Okay, great. So now we're at the results. Actually, Alex was supposed to talk about this, but unfortunately, I think he's not feeling well and he's sick, so I'll try my best to kind of go over the results. As we said in the beginning, the build time was around 150 minutes. Actually, after we added the bytecode compiler, we were able to remove the first 2 stages of the compilation pipeline, and that cut the time in half. So you could see that that was actually like a bottleneck in the process, like doing the interpretation and then the bootstrapping the compilers from there. And the bytecode compiler is naturally much faster than compiling with LLVM into the native code. So an identity function compiles roughly 1,000 times faster. And it's actually better than CLisp on most benchmarks, which we'll see in a graph on the next slide, I think. And well, this refers to the next slide, but you'll see. It's also comparable to ECL. So yeah, here are the bars. The red is CLisp, the yellow is ECL, and the blue is VM, but that refers to the VM that's now used in class that we've been talking about. There are some oddities here. For example, it's kind of variable. Like in the previous slide, it does better than CLisp on a lot of things, and it's just kind of better on some things, not as good on some things for ECL. But what I really want to point out here is that measurement is really hard, because imagine you have these are the Gabriel benchmarks. It's probably testing array, float arithmetic, whatever. These are runtime things. Like the compiler has actually had very little influence on how fast your array library goes. Maybe if there's a matrix multiplication here, like who cares what the compiler is doing? So it's actually extremely hard to separate out what the compiler is doing from your other runtime functions. So this is a very coarse analysis of what's going on. Perhaps we actually do have one result where we know some decision we're making in the bytecode compiler does have an influence on this, which is the cell thing. We turned off the cell optimization, which is eliding cells when you don't need them in the bytecode compiler, and then we turned it on. We actually did see some significant results for a few benchmarks which relied a lot on closures. So there are certain optimizations, there are certain strategies you use in the bytecode compiler that have an actual visible effect on real-world code. But in general, it's very hard to figure out what is actually because the bytecode compiler is better or not. Because these are different implementations with underlyingly very different implementations of array, vector, references, list functions, sequence functions, things like that. And the compile time seems to be in the ballpark of I don't think the compile time is actually amazing. This is also still a work in progress, but I don't think the compile time blew things out of the water compared to the other compilers, which is a bit sad. We were kind of expecting, for example, CLisp does a lot of optimization passes. We were hoping that because we have such a straight line strategy, it would have shown more of a difference. But we did notice something interesting, which was this. It did some profiling, and it turns out that because the compiler doesn't do that much work, we found bottlenecks in places you wouldn't expect. So for example, when you're compiling code, we found that 40% of the time it took to compile some compile benchmark was actually just gensim, like creating a symbol. Because, I don't know, macro expanders call gensim a lot. So these kind of point you to things where, oh, our implementation of gensim is slow. That's why the compiler is slow. It's not, some bytecode compiler algorithm we used. And we don't actually have that much time. There's these last 2 slides sort of are what we can do with the bytecode compiler now that it's done its job of speeding up the bootstrap process. There are a couple things you can use the bytecode compiler for. I'll actually skip this one because I don't know too much about it. But there's this potential application for sandboxing, which is that you can do first-class environments safely. You can use the bytecode compiler as like a kind of a sandboxed environment that doesn't ever touch native code. This is really important because when you're running native code, it can potentially be unsafe sometimes. But when you're running on bytecode, there's kind of less room for doing tricky things that can corrupt memory or execute untrusted code. So that's kind of why bytecode is kind of helpful. And then there's also this idea of cross-compilation, which is that if you can isolate your environment from the host, you can even skip the other steps in the bootstrap process. If you guys are familiar with how SBCL bootstraps itself, it does not bootstrap itself from C, it bootstraps itself from another Lisp compiler. So we were thinking that we could potentially use the bytecode compiler to do cross-compilation as well. And I think this is probably the most exciting application for a bytecode compiler. There are a lot of compilers out there, for example, JavaScript compilers, WebAssembly, Julia, for example. They all have some kind of just-in-time where you don't necessarily compile the best, most optimized version up front. You compile maybe with a faster compilation strategy, for example, bytecode. And then as the page is loading on JavaScript, for example, you then install the full-blown native compiled version. And I think that's a very interesting use case of this because when you're compiling, let's say, a user interface library, everything's in bytecode at first. It goes very fast. You can iterate very quickly in development. Once you detect that this function is really on the hot path, the compiler can figure that out and then install the native code version. So this is already a technique used by a lot of other languages, and I don't think it's used that much in the Common Lisp world. So it would be great to sort of use bytecode compilers for that. So that's something that still needs to be investigated. We listed Hotspot, JVM, V8. Kind of, we can get some ideas from these guys. Yeah. And then I think kind of that's time, right?
Yeah.
Roughly. Okay. So this is where the repository is. If anyone wants to check it out, there's also a specification for the instructions, documentation on how the virtual machine runs. If people are more interested in how we actually design this. And I'll take questions, I guess. Alex is also on the call. I'm not I think he is. Is he able to?
I don't know that we want to do the switching now.
Okay. Or I just mean like for questions, if we're going to field questions. But I think there's too much latency, so I guess
Yeah.
I'll field questions if anyone has them. Yeah.
I have a question regarding safety and the isolation thing.
The sandboxing. Yeah.
For instance, is it possible to restrain things like the declarations of dynamic extents or types? I mean, to not give the possibility of unsafe code so that the isolation is really, really secure, really unable to break out of the box.
I think the bytecode compiler will just ignore dynamic extent and things like that. So, yeah, I mean, there's also the thing where it just does less optimizations and there's less chance for it to do things that could potentially cause crashes or corrupt things. Yeah.
I ask this because bytecode does not invalidate, assuming that, for instance, a variable is a naked pointer or something like that, or a naked double value, whatever.
Yeah, okay, oh, and so I'll just repeat the question also really. So the question is that whether bytecode can, whether using it, for example, can protect yourself from things like naked pointers or other things that could potentially corrupt the heap. And I would just say to that essentially like the bytecode compiler just it runs pure Lisp code. I don't think it will handle C++. Like if it'll handle things like raw pointers, I think that's left with the native compiler. So I think this isn't implemented yet, but I guess the idea would be that the things you're running on the bytecode, kind of by design, will not run things with naked pointers or things that could potentially mess up the running Lisp environment.
No FFI or things like that.
I mean, we don't. It's not implemented yet, but I guess that would be one way to sandbox it. It's just not even to have it be accepted.
Yeah, so the last point that you mentioned with the techniques from V8, well, I don't know V8, but I know SpiderMonkey, and they use bytecodes there to go to the JIT then for inline caches. That's what you meant you would like to incorporate in the future.
Yeah, so the comment question was about how in SpiderMonkey and other JS WebAssembly engines, they actually use bytecodes to do inline caching. And yeah, actually, there wasn't that much time to talk about this, but we had this idea of having the bytecode also be a sort of intermediate representation that you could directly compile native code from. And for example, you could imagine that in the Common Lisp object system, for example, you have discriminating functions at first in bytecode, and then only when you detect that something with types is being called a lot, depending on the call history, then you lower it down to native code, and that can give you extra flexibility in the domain of compile time to execution speed. Dynamically. So I think that would be kind of similar to how inline caches work in WebAssembly. Yeah.
Thank you.
Yep.
So this is implemented, so you also have a virtual machine interpreter for the bytecode?
Yes, actually this is, I didn't go in too much detail about how the form this takes, but essentially we prototyped this with in pure Common Lisp, with a pure Common Lisp virtual machine. And then the compiler was simple enough from Lisp that we just did a direct translation to C++ and for the compiler. And then the virtual machine, what good is C++ for writing things like this, like virtual machines and things? So then the virtual machine is also written in C++, and it's very simple because I think there are 57 instructions or so in the virtual machine. So it's just basically a case dispatch loop, and you run the semantics. And the runtime is also written in C++, so it was actually easier to write the virtual machine in C++ than Lisp, because Lisp doesn't necessarily have the all the raw pointer object machinery that you would want to emulate something like that.
Have you thought about using like threaded code or something to make the interpreter faster?
Are you talking about using threaded code in the context of?
So it's a phrase for virtual machine implementation. It's like the dispatching loop can be made a little bit faster by changing how you do the
you mean like, okay. So the question is whether we can use threaded code to speed up the virtual machine implementations. I don't think we've actually thought about that, and that's a good point. We have looked at the assembly code generated by the virtual machine and how it does the dispatch. For example, I think in C++ it compiles it down to just a jump table, but that might be actually an interesting avenue to look at to squeeze more in. I don't think the bottleneck is actually the dispatch loop in the interpreter. I think there are other issues that need to be taken care of on that side. But yeah, that's a good point. Yeah, there might be ways to get the dispatch loop even faster. And you always think about things like instruction cache too. When you're working at this level, things like instruction cache and like how big the dispatch loop itself is, or whether you should split it up, actually becomes relevant.
There's a question from the chat, which is, would it be easy to retarget a compiler to other IRs, such as Java bytecode or .NET IR?
So I don't have to repeat it because it's from the chat.
Yeah, that's fine.
Okay, so yeah, it's a good question because we kind of mentioned this already, but if you have a bytecode IR, if you have bytecodes, you can use that as kind of an IR that you can transmit to other things. It mostly preserves the semantics of common Lisp. There's nothing specific to a architecture, for example. There's nothing specific to an operating system in the bytecode. It's really just handling the control semantics and the data semantics of the common Lisp special operators. So if you wanted to then lower this down to the JVM, the information's all there. There's not too much information that's too specialized for an architecture, an operating system, or whatever that would hinder that.
I think we're out of time.
Okay.
Thank you.